Okay, welcome everybody. So this is the second of the preparatory lectures, which will be given by Kausik Ghosh, and he's going to tell us about conformal field theory dynamics. Kausik.
Yeah. Okay. So welcome everyone. So I will talk about conformal field theory basics, and I will focus on uh, the dynamical part of conformal field theory. And so yesterday Parthiv covered the kinematical part, and let us start briefly reviewing what he has already told us. And before that, the references that I have followed in preparing this lecture is these two famous references. One is the lecture note by Slava Richkov, and another is Tasi lecture by David Simon Staffin. Okay, so let's start. So yesterday we saw that here as an endpoint of a RG flow. And so therefore it's very important that we understand the properties of CFTs. So that will also help us to understand QFTs, because QFT would be a flow between two fixed points. Not all CFTs have a description like this as an endpoint of RG flow. Um, so we need some non-perturbative definition of CFT, and Parthiv also defined what that means. Roughly speaking, he said that we can define the CFT by its field contents. Okay, and we also saw that there are conformal killing vectors which form a closed Lie algebra, and that was isomorphic to SOT plus 1, 1. Okay. Um, and we also saw that so we saw that there are two irreps of the stabilizer subgroup of the origin, and they are called primary and descendants. We will see that these fields will play an important role in our discussion. And we saw that using the invariance under full conformal group, we can fix the form of the 2-point function and the form of the 3-point function completely. So if you see here, then if you take two fields, then the 2-point function is only non-vanishing when the dimension of those two fields matches. Okay. Uh, Now we consider the 3-point function, and the 3-point function was fixed. The coordinate dependence was completely fixed up to a constant, which is called OPE coefficient. Okay. And then we saw that the 4-point function was fixed up to an arbitrary function, which I wrote here as G. So this is an arbitrary function of U and V, and UV are the conformal invariants. Okay, the conformal invariant quantity that you can make out of these 4 points, x1, x2, x3, x4. So this G is not fixed. Unlike 2-point and 3-point function, the coordinate dependence of 4-point function is not completely fixed, right? So this was the thing that we saw yesterday. And today we start with quantizing the CFT. Um, and as we go along, we will see what are the dynamical quantities of CFT that we would like to compute. Okay. All right. So let's start. And in case anyone have any question, please feel free to ask, because I will not. I can't see anyone, so I will not know. Okay. So typically in QFT, we usually quantize our theory on a constant time slice, right? So we take a space-like surface at a particular instant of time, and our Hilbert space lives there. And then we use we take our Hamiltonian, which generates the time evolution. So this basically, if you think of the space-like, there are some space-like surfaces, and the one surface is connected to another one by this time translation, and which is generated by the Hamiltonian, right? And because of the fact that all the momenta, they commute with each other, so therefore the states that leaves on the Hilbert space those are characterized by the eigenvalue of the momentum operator. So that is the energy and the momenta of the state. Okay. All right. So in CFT, it turns out that though this is possible to do exactly the same thing, but to see many properties of CFT which are useful, it turns out that there is a, different kind of quantization, which is called radial quantization, and that turns out to be more useful. Okay. Uh, what is done is that we foliate the space time by this. If we are in d-dimensional space time, then you can imagine that these are the d-1 dimensional spheres, which is at some radius r. And then you can think of the evolution of one sphere to another is generated by the dilatation operator. Okay. So this is basically the scaling operator, right? So yours, then the point is that your Hilbert space will be so the Hilbert space will be associated with this d-1 dimensional sphere at a particular radius. Okay, so this is how we quantize our theory. Um, now, just like previously, all the momenta commute among themselves. So therefore, we characterized the state of the Hilbert space by energy and momentum. Here you can see that the dilatation operator commutes with the rotation operator, right? So therefore, the states on the Hilbert space will be labeled by two quantities. One is this delta and another is this L, where delta is the eigenvalue of this dilatation operator. So that is like energy of the state, and the spin it will be characterized by the spin, right? So that is the representation of SOT. So all the states on the Hilbert space will be labeled by these two quantities. Okay. Uh, and one can see that yes.
Uh, the d delta ls, that changes the state, or is it a typo?
D delta LSS. Oh, no. That's a typo. That will be same as here on the left.
Also, the d p mu commutator was minus I p mu. You have written p mu.
This was minus IP mu. Okay. So I have missed it. Yeah. It should be written as like just it should be proportional to p mu. That's what is important.
Okay, fine.
Yeah. So d p mu commutator should be proportional to p mu.
Could I ask a question as well?
Yeah.
So in the first operator equation, you have written down d on the state gives us I delta, right? The eigenvalue is delta.
Right.
Second equation, we have the sigma mu nu.
Yes.
Right.
So
yesterday.
Yeah.
So yesterday in Pathiv's lecture, we also saw like the representation on the origin, like the operator representation on the origin were also delta and sigma mu nu. Are these the same, or is that just
so they will turn out to be, there is a one-to-one correspondence between the states on this Hilbert space and the operator at the origin that will come to, but for now these are just some independent states that I am defining. And then indeed, as you said, that you can relate this to the operator at the origin, so that's called state operator correspondence.
Okay, perfect, thank you.
Okay, so I thought that Parthiv defined the commutator like this, but maybe I'm mistaken. So there could be a difference of I, that's possible. So what matters is that the D commutator P mu should be proportional to P mu, such that when you act P mu on a state and you use the commutator relation between D and P mu and write it like this should increase the energy by 1 unit. Okay. And because of the commutation relation like this, what will happen is that when you act on your state by k-mu, and you measure the energy by acting with d, and you again use the same commutator, and you should see that the energy will be decreased by 1 unit. Okay. So these are the two facts that's important to remember, that if I act with the momentum generator on a state, then the energy of that state is increased by unit amount. And if I act with k-mu, then the energy of the state decreases by the unit amount. So that's why this name you can associate, you can sort of see like these are like the raising operator and lowering operator that we see in the harmonic oscillator case. Okay. Um, so another way to visualize this radial quantization would be if we map from d-dimensional flat space to on a cylinder. So suppose we start with in a spherical coordinate. So the coordinates are written in spherical coordinates. So this is my flat space metric. And then I can write it down, like I can take this r square common, and I can write down this thing on the bracket like this. And then I can take, suppose r is like e to the power tau, then this particular quantity would become like this, right? And you can see that this is nothing but these are the metric on a cylinder, right? So you should notice that we can write down the flat metric in terms of the metric of the cylinder up to a scale. So therefore, we can see that cylinders are conformally flat, right? So they differ by up to a scaling factor, right? So this is like Weyl transformation. But you should remember that these are the symmetries of, these are the conformal transformations. So therefore, if you define some correlator here on the cylinder, then those will be related to the correlators in the flat space by some overall factors, right? That we saw yesterday, we'll see that again today.
Is it a cylinder or a boundary of a cylinder?
Sorry, what?
Is it a cylinder or a boundary of a cylinder? The cylinder is like dr square plus r square d omega square. This is right.
No, this one
Maybe
is this one
no.
is sphere. This one is sphere.
Okay. No. Yeah. Okay.
Okay. All right. So okay. So you can see that why we do this. So till now, if you see that you have a suppose you had a sphere of radius r, and you act with you evolve with this operator, then basically what you are doing is you are rescaling the r to some e to the power lambda times r, right? So then if you use the mapping that we have wrote here, that r goes to e to the power tau, then using that you can see that on cylinders it just means that tau goes to tau plus lambda. So it just becomes the usual time translation we see in our usual quantization picture of QFT, let's say. So this becomes like time translation, right? So therefore, going from one sphere here on the flat space to another sphere is same thing, like at a particular cylindrical time slice, I can take a sphere. So this sphere will map to a sphere on this cylinder at a constant time slice, cylindrical time slice. So tau is the cylinder time on the cylinder. And then the another sphere will be just related to initial sphere by some time translation, right? So therefore the radial quantization can be viewed as, you can see, you can think of it like the usual quantization on this cylinder. Okay. So and indeed, as I said that whenever the metric is related to by some overall factors to your actual metric, then these kind of under this kind of Weyl transformation, the correlators are they are related by some overall scaling factors. Okay, so this particular relation we saw yesterday also, right? Um, so what we can say is that from this, it is clear that so if we take a scalar field on the cylinder, so that will have coordinate, say tau comma n vector. N is just the unit sphere metric coordinates. So that field will be related to my flat space scalar field by a overall uh, scaling factor, which is r to the power delta phi. Okay. So what I can do, I can compute my flat space. I can just compute my cylindrical, let's say a cylindrical correlation function on a cylinder, and then that will be related to the flat space correlator by some overall factors, right? And one thing to notice is that so because of the fact that here the time translation becomes the symmetry of the on the cylinder, therefore if we compute the correlation function on the cylinder, then it has to be a function of the difference of the time coordinate, right? So that is the tau, difference in tau. Okay. So next, we come to the state operator correspondence, and this is related to the question that initially, like towards the beginning, someone asked. So here, what we are trying to say is the following: that suppose you want to write down a wave function, okay? You want to write down a wave function for some field configuration, let's say here on this second sphere, okay? So this is, let's say at tau f, there is some field configuration given, which is like phi f. And then you want to write down a state psi, and then how it is related to a state which is here in this inner circle, innermost circle. These are actually sphere. So innermost sphere, suppose there a field configuration is given, which is phi I, and you know the state there, okay? So you write it like psi phi I tau I, which gives you the state on this sphere. And then you want to write down a state on this bigger sphere, evolving from which is evolving from this state, okay? So then what will you will do is that you will do a Euclidean path integral over this annulus region here, um, and uh, and that's it, right? I mean, these are the standard path integral that we do. So but this is schematic, of course. I mean, here what I have written is schematic. So suppose you have some scalar field, then basically you are integrating over all the scalar field configuration in this region, satisfying the boundary condition that the field configuration on this boundary is given by phi I, and on this outer boundary it is given by phi f, okay? And then you are basically integrating over all the field configuration at your initial state. So that is what this wave function looks like for a state here on the second sphere. Okay. Now suppose you send this initial state to your center. Okay. So let's see this picture. I mean, where it would be more clear. So basically, initially you have a state here, which is at tau equal to 0. Okay. So now you want to send tau goes to minus infinity. So that basically maps to r equal to 0, right? So what is happening is that if in this Euclidean path integral language, you have to specify boundary condition on the so boundary condition means basically the field configuration on this boundary, space-like boundary at tau equal to minus infinity. But that is same as stating a boundary condition at the origin, right? Because this point maps to the origin. So therefore, you can see that you have to here on the cylinder, actually you have to specify the full boundary condition on the entire space-like boundary, whereas here you have to just mention in this picture you can see that you have to just give the local condition at r equal to 0, right? So therefore, this is what the operator insertion means, right? I mean, instead of entire, some non-local boundary condition, now you just have to mention the boundary condition at a point, right? So therefore, what the first Euclidean path integral that we started with, that would become something like this. So you are just inserting an operator at the origin. You are just inserting an operator at the origin, and then you are integrating over all the fields that is inside the sphere, and that will give you a state on this blue sphere. Okay, so this is what is called that there is a so for each state on this sphere, you can think of a mapping between that and an operator, a local operator, which is at the origin. Okay, and they are related by some path integral like this. Okay. So anyone have any question at this point?
There are two integrals, right? Over d phi and d phi I. You're just
So here you can think you have to. So this integral means that you have to integrate over all possible values for this operator, right? So right now this is just at a point. Now this operator can take any value, and under this integration, when you are integrating over all the field configuration, you have to integrate over all possible values that this field can take on the origin. Okay.
Okay.
Yeah. Okay. So we learned that for each state on this sphere, we can insert an operator at the origin. Okay, so this is the state operator correspondence. So let's see what are the consequences of this. So for example, the vacuum state on the sphere, you can think of it as inserting nothing, which is basically just the identity operator. Okay, so that O at 0 is just replaced by an identity operator. So that will give you the vacuum state on the sphere.
Yeah, there's a question in the chat box, Kausik. We haven't specified a Lagrangian for the CFT. So then what is S phi?
So this is just schematic representation for for our understanding. I mean, this is not like yeah, if you so we are assuming that, let's say there is some field configuration, we know what is the probability for the like, so so what I'm trying to say here is that this is schematic. I mean, this is not really, but if you have a Lagrangian, then you can define like this. This is one way to see that there is a state operator correspondence. But yeah, but this is true for even in an abstract way for any CFT. Yeah.
So we don't really need the action to define the state operator correspondence. Is that what you mean?
Yeah.
Okay.
Because indeed there are CFTs where you don't know what the Lagrangian is, and then what is the path integral you should write. That is true. Okay. But here we are just trying to I'm trying to motivate like how the state operator correspondence work. But I'm saying that this works for any CFTs which has Lagrangian description or not.
Right.
So okay, so then we can also define a state, say delta on the sphere, and then that is equivalent to like acting with some operator on the vacuum. So therefore now you are basically integrating over all by your weighting factor is this field at the origin. So this state on the sphere is they correspond to an operator at the origin. Okay, so this is the mapping, like the vacuum gets mapped to identity, a field so this kind of state gets mapped to operator at the origin. But suppose now you have a state which is like this, and then that state is let's say not at the origin but at some random point x. Okay, then how should we look at this particular state? Okay, so we have already learned about primary states and descendant state yesterday. So we will see that those description will now be useful. So for example, suppose, so you can write down this O delta X in this form, right? So now e to the power minus IPX acting on vacuum is just, it will give you back the vacuum because vacuum is invariant under the momentum. So if the action of momentum generator on the vacuum is invariant, so this is translation in invariant. So therefore, this will just give you the get vacuum again, and then O delta 0 will act on the vacuum, and that will give you the state delta. And then e to the power IPX, this operator will act on the delta, right? And then I can expand this operator, and I can write it like IPX to the power n by n factorial. This is the usual uh, expansion of exponentials, and then those will act on the state. Okay, so what kind of state we will get? We will get a state like so something like where the p mu acts once on delta, then twice on delta, and so on. So I will get a state which is a series like this, where the momentum operator is acting on the state multiple times. Now, so now this O delta 0, this is what actually I am assuming is that these are primary fields. Okay, so therefore they diagonalize under the action of dilatation generator. So therefore, this P mu acting on delta, and these guys, these are nothing but the descendants of that primary field, which is O delta 0, right? So these are, so P mu is basically del mu, so derivative acting on the primaries. They give us the descendant, which we saw yesterday. And then this is basically generating a series of descendants for my primary operator, O delta 0, at the origin, right? So therefore, what we just saw is that this kind of fields are can be written down in a basis of primary operator plus its descendants. So these are not the eigenstate of dilatation operator, rather it's a combination of this primary state and its descendants. And indeed, like this, we have already seen that if momentum operator acts on the primary field, then the energy increases. Therefore, if it acts n times, then the energy will be delta plus n. Okay. And similarly, we have also seen that action of K mu on the primary operator on a state which is which gets mapped to a primary operator at the origin. So that state will have energy which will be less. So this lowers the dimension by 1, and therefore, suppose you keep hitting with K mu on this state, then essentially what will happen is that one particular thing that we will see just after this is that in unitary theories, the dimension has to be bounded from below. Okay, otherwise the norm will be negative. The norm of the state, the scalar product between two states, will be negative unless the dimension are bounded from below. So therefore, if you just keep hitting with any operator with this K mu, then there will be a point where it will because since you are decreasing the dimension by 1 each time you are hitting with it, so at some point it will give you 0, right? Because it is bounded from the below. So therefore, you can see that those are nothing but our primary operators, because by definition, if the operator vanishes under the action of K mu, then those are my primary operators. Okay. So now I was talking about norm. So therefore, we need to understand what is the Hermitian conjugation in this radial quantization. So remember, I have a field on the cylinder, which is this, and then I want to take Hermitian conjugate of that. So I first wrote down it like this. So this is just the time translate. So basically, this is the evolution operator for this field. And then I'm taking the Hermitian conjugation of that. So that will give me this, right? And this is nothing but you can see that this is field on the cylinder, but uh, but the time tau has been deflected to minus tau, right? So therefore, in this geometry on the cylinder, the Hermitian conjugation operation on the scalar field, you can see that tau gets mapped to minus tau. Okay. So suppose you are interested now that you take this phi tau n vector. So this is your operator, and you are acting on the vacuum, and then this will create a state, and you are interested to know the norm of that state. Then you have to take the scalar product of this state with its conjugate, and which is this, and therefore you get a configuration like that, right? So this has, so the time gets reflected to minus tau. So there is a reflection transformation of cylindrical time. And now you can see that if you demand positivity of this, then this will actually correspond to the positive norm for the states on the cylinder. Okay. Um, anyone has any question at this point? Okay. So so now you can also see that what it means on the flat space. So tau gets mapped to minus tau on the cylinder. So that operation is basically taking an inversion on the flat space. So on your flat space, what is happening is that your x is going to x by x square. So this is basically x mu goes to x mu by x square. Okay. So this is the inversion that is happening when your tau gets mapped to minus tau. So therefore, the statement would be that flat space correlators with operators inserted in an inversion symmetric way that computes the norm of the state in the radial quantization, right? Because we just saw that tau goes to minus tau under that. So if we just symmetrically insert operators in time, then that computes the norm of a state. So therefore, if I consider flat space correlator, then I have to insert the operator in an inversion symmetric ways, because tau goes to minus tau is like a inversion symmetry, inversion transformation on the flat space. So that will compute the norm of the state in the radial quantization. This is the statement. Okay. Yeah.
Can I,
Yeah.
sorry for bombarding you with questions, but
No.
in radial quantization, we had the dilatation operator as the time translation thing, right?
Yeah. Oh, you are confused about this age. This age
Yeah,
is
yeah.
nothing but D. That's a proxy
Okay.
for D.
Okay.
Yeah.
Okay.
Yeah. Sorry about this. Yeah. That's just proxy for D. You are absolutely right.
Okay, so this is a doubt basically.
Yeah.
So usually Hamiltonian is associated with the P0, right?
With the P0, yes.
So why is in this case you say D measures the energy?
No, we are not. We are not actually quantizing our theory on a time like or on a space like surface. So what you are saying there, I have to fix. So at a particular instant of time on a space like surface, we quantize the theory. You have to understand that here we are not doing that. Instead, we are quantizing our theory on a sphere of d minus one dimensional sphere. So this is a different quantization from what you are saying. Now, what you are saying, that can also be done, but the things that we will get out of what we will see just now, those are not obvious in those quantization. But it's not that those that doesn't exist. I mean, you can also do that that way as well.
Okay.
Yeah. This is a different quantization. We are, yeah. So in this quantization, you can see that here the time evolution in our original coordinates in the flat space is basically the scaling operation. So therefore, it is the evolution happen is generated by the dilatation. not the Hamiltonian, because there it's the time translation. But if you see the picture on the cylinder, then it becomes very similar to what you are saying. With the, of course, I mean, still we are doing the same thing. We are just computing the same thing, but in a different geometry. But at least on this cylindrical geometry, the time translation becomes a isometry. You can see that it just goes to tau plus lambda. So therefore, in this geometry, D is like literally the behaves like a Hamiltonian of the system. Okay. Uh, okay. So we have seen that the phi cylinder, so a scalar field on the cylinder related to a scalar field in the flat space on the flat space by a trivial scaling factor. And you saw that phi when I take the Hermitian conjugation operator of this cylindrical field, the field on the cylinder, just tau gets changed to minus tau. And if you just use that relation, then you end up getting this, that the flat space, when you take the Hermitian conjugation of the flat space field, that will transform like this. Okay, so this would mean like this. And if you remember, like this is nothing but the inversion. So that's what we said, that in flat space, you are basically inverting your, you are doing an inversion. Okay, so x mu goes to x mu by x squared. Okay, and but this conjugation also will act on the, so this, we also need to know what is the conjugation of the generator itself, right? I mean, it will act on the fields, but at the same time, you can also take Hermitian conjugation of the generator itself. And they also changes like under the action of, so this Carly I is basically inversion. So this is an operator. So you are basically doing an inversion, and then you are doing the translation, and then you are again doing the inversion. So basically this operator is transformed under inversion, and that gives you the Hermitian conjugation of that particular operator. Okay, so here I have written down it for the momentum generator. And if you have noticed, then yesterday, when Parthiv was explaining this, so then you could have seen that P mu is a translation which basically changes, which translates your origin, right? So if you do a translation, then your origin will shift to somewhere, but your infinity will remain at infinity, right? So infinity doesn't change, but the point at the origin, that gets translated. But K mu, so K mu is, so this special conformal transformation is a transformation which actually generates translation for the point at infinity, and it actually keeps the origin fixed. Okay, so therefore, if you notice, then when you do this first inversion, then what will happen is that your origin will go to infinity, and the infinity will come at the origin, right? And now P mu will translate your origin, your new origin, but this was actually the infinity in your initial configuration. So therefore, you generated a translation for the infinity. But you should remember that the zero, the origin of your initial configuration, that has been mapped to infinity. So under this P mu, that will not translate. And then you again do an inversion. So your infinity come back to the zero, right? So therefore, your origin doesn't move under the action of this kind. And therefore, you recognize this particular combination of transformation as the K mu. So this is an important result, that if you take the Hermitian conjugation of momentum, then that will that gives you the generator of special conformal transformation. Okay, and this you should not be very surprised. For example, you can do a small exercise that you can just start with P mu equal to minus I del mu, like the usual one, and you can write down that in this tau, and so on the cylinder. So if you do this coordinate transformation, you can explicitly check that P mu dagger becomes equivalent to K mu, just doing the coordinate transformation. Okay. All right. So I was doing all this just to tell you this slide where we discuss the unitarity bound. So therefore, we are interested in computing the norm of a state. Okay. So suppose there is a state delta, and p mu is acting on this, and then the conjugate state would be this, right? Delta, but this p mu dagger would become k mu. So suppose you just take the 0th component of this guy and you compute this quantity delta k0 p0, right? But the commutator of k and p gives you just d, right? So therefore this would be some quantity which is proportional to delta, and these delta states are normalized, so that's just not there. So this gives you delta. Okay. So now now these are states, right? So you want the norm of this state to be positive. So therefore, this particular computation tells you that delta has to be greater or equal to 0. So this is for scalar, of course. That is why there is no rotation part. It's only the eigenvalue of dilatation operator. So you already get a very interesting bound on delta, that for scalars, uh, uh, for a unitary CFT, the delta has to be greater or equal to 0. Okay. And you can notice that when this saturates the bound, so when delta is equal to 0, then actually it means that P0 acting on delta gives you 0, right? And what does this mean? This means that it just it is invariant under the the momentum generator. So what is that state? I mean, that state is simply the vacuum, right? So therefore, when delta is equal to 0, that basically corresponds to the vacuum state, and by the state operator mapping, this will correspond to the identity operator of your theory. Okay. All right. So now you can do the similar, like you have to use this kind of commutation multiple times. Then if you compute the norm of a state where it's not just p mu delta, but it's like p mu delta, then you will get you will get a quantity like this, and this is again some state. So therefore the norm has to be greater or equal to 0, and that tells you that delta has to be greater or equal to d minus 2 by 2. Okay. And this is again for scalars. All right. So notice now we have a improved bound. So initially we were saying that, okay, delta has to be greater or equal to 0. But now we are seeing that delta has to be greater or equal to d minus 2 by 2 if delta is not equal to 0. Because if delta is equal to 0, then this whole quantity would be 0 again. But if delta is not equal to 0, then delta has to be greater or equal to d minus 2 by 2, which is stronger statement than this bound. Okay. So you should notice that you are already telling about the spectrum of your theory. You are putting constraint on them by using just the conformal algebra. Okay. Okay, so this is again for scalars. Now you can think, okay, so can I act with 3 or 4 or more generators on this delta and see if we get more stronger bound or something like that? It turns out that you can't improve this. I mean, from this kind of exercise of demanding that the norm of the state should be positive, you only get this, that delta has to be greater or equal to d minus 2 by 2. This is for scalars again. And you should notice that when delta equal to d minus 2 by 2, then that simply means that p square delta has to be 0. But then that is nothing but p square, and there is some operator at the origin, and that should be equal to 0. So this is this you should notice as the equation of motion for the free massless scalar field, right? So therefore, this scalar field would be essentially free if delta is equal to d minus 2 by 2. This also you can see from the simple power counting, right? Okay. So these are the bounds for scalar field. You can also consider fields with integer spins. And there also you can do a similar exercise. You have to do a little bit more than what you have done before, but it is also fairly simple. And if you do that, you will end up getting this result, that for all the traceless symmetric fields, that is the fields with integer spins, the dimension has to be bounded from below by this quantity L plus d minus 2. And you can see that when delta equal to L plus d minus 2, it just simply means that p mu acting on that spinning operator gives you 0. So that is simply del mu acting on a spinning operator 0. And let's consider some spin 1 object. So therefore you can write it like some j mu. So del mu j mu equal to 0. So you can see that this is telling you that whenever this bound is saturated, that is nothing but some conserved currents of your theory. So if you have such an operator where the spin is greater than 0 and their dimension is given by this, then you should you should immediately notice that those are the conserved currents of your theory. Okay, so these are the constraints that you can derive using the conformal algebra, and this puts bounds on from below on the dimension of the fields. Okay. All right. So the next thing is operator product expansion. So what it tells is that if we have two fields, let's say phi1 and phi2, then we can replace the product of two fields by an infinite sum over operators. And these are local operators. You should notice these are local operators. And this function, cox comma delta, this is basically the function of x, and these derivatives are will act on this field, and that will generate essentially the descendants of your theory. So this sum is over only the primary operators of your field. Okay. So but you should notice that this is an infinite series, and this, so therefore there might be a problem with the convergence of this series. And that is indeed true, because in QFT this series sort of makes sense only if x is very close to the point 0. So if these two operators are very, very close to each other. But it turns out that in CFT, this is convergent even when x is not close to 0, x is not close to the origin, but separated by some finite distance. Okay, we will see like what exactly is the condition when this operator product expansion converges. But the non-trivial claim is that in CFT, this sum is convergent under even when x is, the two of the operator is finitely separated from each other. Okay. All right. So the proof of this fact follows from the following thing, that suppose you have two operators, phi1x and phi2 at 0. Okay, so phi1 is at x and phi2 at 0. Then immediately you can associate a state on a sphere, which is like this. So these two operators acting on the vacuum and creating some state psi on the sphere, right? But then psi on the sphere, any state on the sphere can be expanded in primary and descendant fields, because that primary and descendant, they form the complete orthonormal basis on the Hilbert space on the sphere. So therefore, any state that you write down on the sphere, you can break it, you can expand it in this basis. That is the primary and the descendants. Okay. And then you can rewrite this. So you should notice that descendants are nothing but the p mu's acting on the primary operators. So therefore, this expansion, you can repackage something like this, what I have written here. So basically, you should notice that this is some function which has derivative in it, and that is acting on the primary fields here. But then these fields, these particular states, are nothing but some operator which is inserted at the origin. So because of the state operator correspondence, we immediately see that the two product of operators can be replaced as sum of local operators. But you should also notice that all these things, so you have to be worried that when this kind of expansion is okay. So when is it okay? It's okay when you can draw a sphere, inside which those two operators are in of which you are interested to compute the OPE of. Okay. So basically, if you are interested to compute OPE of this field and this field, then you should be able to draw a sphere without crossing without including any other operator while drawing the sphere. So if you can draw a sphere like this, you are done. Okay. So the proof of this statement follows essentially this way, that suppose you have a state psi, and then there is so this is some outer state, like psi, and then there is phi 1 phi 2. So this psi is a proxy for all other operators that is here, so that will create some out state on this sphere. And this phi 1 phi 2, which is inside the sphere, that will create some in state, let's call that xi. And then you are just computing the inner product of psi and xi. And this field you can expand in the orthonormal basis of your so as you know that the eigenvector of dilatation operator, I mean they and their descendants form a complete set. Therefore you can expand them into orthonormal basis, and that expand when you do that expansion and take the inner product of them, that is a perfectly well defined quantity. Okay, this is a theorem on the Hilbert space. I mean, in the Hilbert space, if you break it into orthonormal basis, then this inner product will always converge. So therefore, OPE converges as long as you can draw a sphere to separate two operators from all others. Okay, so if you can do that, the OPE always converges. Okay, so is there any question at this point? Okay. All right. So let's see an example how to compute the operator product expansion. So suppose you have these two operators, then operator product expansion tells you that it will be some local operators on which some derivatives and the function of x, this x and derivatives will act on this guy, right? Now in the small x limit, you can expand this function and you get something like this. These are the first two terms that I have written here. And I'm thinking that the primary, so you have to sum over all the primary that you have in the theory. Let's say we are interested in computing this for a scalar field. Okay, so this O is a scalar, let's say. So for that scalar primary, if we expand this function around small x, then you get in the first two orders, you get something like this, right? I mean, this is just leading order in x, and this is linear in x, and there are other terms which are basically the other descendants of the field phi delta 0. Now so you can see that there are a couple of things which are unfixed. For example, there is this c sitting outside, there is this k, and there is this lambda. So these are the three things that are unfixed, and probably you would like to fix them using the conformal symmetry. Indeed, you can do that. For example, you can act with the dilatation operator on the state, and then we know that the action of the dilatation operator on the field phi 1 at x is given by this. So this is just the commutator of these two operator. And then when you have to add the other piece, so when d act on phi 2, it just gives you delta 2, right? And then again, what you have to do is that now you see that your things have been arranged in this form, that phi 1x, phi 2 0 acting on 0. And then here also the same thing. Now you use this expansion. Okay, so instead of that, you write down this part. And when you write that part, then you get, and then you take the derivatives and you get something like this. Okay. So this is the thing you get when you act D on this state. Now you take directly the right hand side of this equation, okay, and act with D. So when you act with D on this equation, you can see that this is just some complex number, and this is a generator. So this is an operator. So therefore it will not act on this. It will directly go and it will act on the phi delta piece, right? So then that will just give me, since this is a primary, so therefore it will just give me the eigenvalue, the conformal dimension. And if you compare these two sides, then what you get out of this exercise is that k is given by this quantity, which is delta 1 plus delta 2 minus delta. Okay. All right. So so this is how we fix the k. Now you can act with K-mu and follow the same algebra that we did above. Just here you have to use the fact that the K-mu commutator phi1 is a little more complicated. And when K-mu will act on phi2, since phi2 is a primary of your theory, this will just give you 0, right? But then you can indeed compute this in the similar way, and you will get this from the left-hand side. And from the right hand side, again, the K-mu will just go through this and it will hit the phi delta. But since this is a primary, it will just give you 0. So it will hit directly here. And then what you have to do is that you have to write down this delta nu as something like p nu, and then you use the commutation relation between k mu and p nu, and that will essentially at the end give you this. Okay, this is details. I mean, not necessarily you have to follow this, but the point of this is that you can do this exercise, and at the end you get this lambda. Okay, so if you see now, then you can see that you have almost fixed like all the unknowns up to this leading order in X, up to this linear order in X. But this C, there is some overall constant C which you can't fix. Okay, so it will turn out that you can't actually fix this overall constant, and this will be related to the OPE coefficient that we saw in the 3-point function in our initial slides or yesterday. Okay, so one way to see this would be the following, that like if you consider, so this is like another way to compute the OP, and this is the easier way. Like here you can see that you have to act with different generators, then use the commutator, and if you go to higher orders, it's really hard to do this computation. Rather, the easy trick, one easy trick would be that take this 3-point function, and inside this 3-point function, take the phi1 and phi2 and consider the OPE of phi1 and phi2. So that you can write like this. So this O comes out of the OPE of phi1 and phi2, and phi z was already there. So you use the OPE once, and this 3-point function will reduce to 2-point function. Okay, but you know that the 2-point function is only non-zero when the conformal dimension of both the field matches, right? So, and also the spin has to be same. So therefore, this is a scalar field. So this 2-point function would be only non-zero if O is phi, right? So then you get that 3-point function. So this sum now only survives when O equal to phi, and then you get this particular relation, right? And this is the C phi x comma delta that you are interested in computing. So now the way to compute is that this 3-point function completely, right? I mean, this is fixed by the conformal invariance. We already saw it. And this 2-point function is also fixed completely. So you just plug this in here, and then you expand this in small x, and you compare term by term, and you match the coefficient. So this is the, this is more systematic way to do this. And you can, of course, consider other fields, spinning fields, and you can see the OP, like the contribution of some spinning primary by using the same kind of tree. Okay. But the whole point is that, which is important, is that when you consider the OP coefficient, the entire structure of this C phi, COX comma delta gets fixed. Only this F120, so which is basically the OPE coefficient that appears in 3-point function, that constant is not fixed. So up to a constant, everything else gets fixed using the conformal invariance. Okay. Okay. So now I will just show some 4-point stuff and like Bootstrap equation, etc. So maybe at this point, if anyone has any confusion, they can ask. Okay. So, all right. We saw that how this OP works. Now, you can see that if you remember in the 4-point function, in the 4-point function, there was a piece which we were calling something like the Scarligi function, which appears in the 4-point function. So that function is completely unfixed, right? So therefore, you want to actually you want to derive some constraint for that function so that you can solve for it. Okay. So in that process, this OP would be helpful. For example, you consider this 4-point function of phi1x1, phi2x2, phi3x3, and phi4x4. And then you can consider the OP of phi1x1 and phi2x2. And you can also consider the OP of phi3 and phi4. Okay. And that you can write it like this, which I have written here. And as we discussed above, this particular part of your expression is completely fixed by the by using the conformal symmetry. So the only thing that is that you don't know is this product of 3-point function. Okay, so product of 3-point coefficient. Okay. So let's okay, good. So this thing where it repackages this whole product of c times this 2-point function, this is called conformal block. Okay. So we will see what this conformal block or how does it look like, but we can expand. So what I'm showing you right now is a partial wave expansion of the 4-point function. So right now you see, like, you have some function, and this in principle, this g delta L u comma v, so therefore you are expanding the 4-point function in this known basis of functions, which we are calling conformal blocks here. Okay. So all right, and you should notice that like I want to introduce this new variable which is zz bar, and so this zz bar is related to u and v in this following way, that u is a product of zz bar and v is a product of 1 minus z and 1 minus z bar. So there are many things that one can do with these variables, like it's easier to do with this variable. So this is just a coordinate transformation, of course, but there is a meaning to it. And to see it, what you can do is that using the conformal transformation, you can actually fix out of your 4 operators that you have, you can actually fix 3 of them, and you can put one of them at 0 and the other guy at 1 and the other guy at infinity. Okay. And then the so let's say I fixed here the phi at x1, I fix here the phi at x3, and I fix here the phi of x4. Then this phi at x2 can be anywhere on this plane. Okay. And the coordinates would be given like this. So z would be given by x plus i2, z bar would be x minus i2. So in the previous slide, when you see this z bar, they are related to your known coordinates in this following, using this relation. Okay. And this is complex coordinate because you are doing this in Euclidean sense. But if you want to go to the Lorentzian time, then you have to put tau equal to IT. And then you will see that z and z bar becomes completely independent of each other. And they are the 2 real variables. Okay. And okay, okay, so this is something that that is important to know, that instead of using u and v, there is a coordinate z and z bar, and that makes life easy with some computation. So I told you that there are these conformal blocks, but you have to know what are those conformal blocks, right? Then you should know a way to compute those conformal blocks. So that is what this slide tells you. That it tells you that you have to consider the Casimir of the conformal group. So Casimir of the conformal, so any Casimir of the group commutes with all the generators of the conformal group, right? And it also acts with the same eigenvalue on every state in irreducible representation. So if you take a state which is in this which is characterized by these 2 numbers, and if you act with C, this gives you an eigenvalue equation where the eigenvalue is this, and this whole times the same thing. Okay. And because of this, you can see that because of the fact that Casimir actually acts on commutes with all other generators, therefore, if you consider any descendants, and then if you act with Casimir, that will also give you back the same eigenvalue equation. And if you have noticed the conformal block, then that was actually computing the contribution to the 4-point function of a single primary operator and all its descendant, right? So there are some primary operator, and then there is all its descendants sitting there. So if you act with the Casimir on the block, then you should get back some eigenvalue times the same thing, because because of this, that Casimir acting on this gives you some eigenvalue equation. So that's what happens, that this conformal blocks are eigenvectors of the Casimir operators, and it gives you this eigenvalue. And because of the fact that the Casimir is written in terms of the generators, and you already know how this generator acts on the operators, so therefore you can write down a differential equation in terms of z and z bar. Okay, so you should see that this is nothing but another way to write the conformal cross ratios at 4-point level, right? I mean, yesterday we were writing it using u and v. Now we have just done some coordinate change, and we are writing it in terms of z and z bar. Okay. And in terms of z and z bar, there is a nice structure of this differential equation. You can see, so this is the differential equation you have to solve. Like, this is the differential of a equation which will act on the conformal block and give you some eigenvalue equation, and you have to solve this, right? And there will be some boundary condition which is fixed. I mean, that comes from the OP, but that is details. I mean, not you don't need to know right now. But the point is that there is a differential equation, second order differential equation, which you can solve, and you can get the conformal blocks. Okay. One thing to notice is that this equation is invariant under the simultaneous transformation of z and z bar. And also notice that when you put d equal to 2, the z dependence and the z bar dependence, they completely factorize. Okay. And similarly, because of this reason, in d equal to 2, the g delta and the conformal block has a solution of this form, where the z and z bar dependence factorizes into 2 parts. Okay. And this k beta x is given by some hypergeometric function. So these are some 2f1s. So so these are the explicit expression of conformal blocks that, so you can take this expression, these are the known functions, so therefore you can expand any 4-point function in 2 dimension in this basis.
There is a question from the chat that how do we get the differential equation?
How do we get the so that actually you have to consider this 4-point function actually, and then you have to act with the Casimir, and the Casimirs are nothing but the operators, the generators, and you already know that what is the action of generator on the fields, and therefore you have to use those differential equations, and you will end up getting the differential equation that is written here. It's a bit of a lengthy exercise, but yeah, it's most easily done using something called embedding space. But yeah, but that is essentially the idea. So Casimir is given by the generators, and you know how the generators act on the fields. So therefore, you will end up getting some equation. If you are worried about these factors, that there will be some overall factors, but you can see that this particular term is this particular overall prefactor is completely known. So if you act with Casimir, you would know what it will give you. Yeah. Is that okay? Okay. All right. So now let me let me talk about the Bootstrap equation. So all that I was telling you till now, so now comes the actual interesting part. So suppose you take these 4 identical scalars, okay, and consider the 4-point. All right. So you can take the OP of phi at x1 and phi at x2, And you can also take the OPE of phi at x3 and phi at x4. And this, you can see we already saw that you can expand this into this block. So this is called S channel block. This is just a nomenclature. And then you can, but you see, I mean, you could have taken any OP of any operators. I mean, you could have brought the x1 and x4 close together and x2 and x3 close together. And then you could have taken the OP of phi at x1 and phi at x4 and the OP of phi at x2 and phi at x3. I mean, no one's told you that you just have to take OP of phi at x1 and phi at x2 and the other two guys. You could have taken this as well, right? And it turns out that when you do this, like when you bring x1 and x4 close together and phi at x2 and phi at x3 close together and compute the OP, you can expand with the same function that appear, with the same blocks that appear here. Only the difference would be this UV would now swapped. Okay, so it would be like V comma U. Okay, and this prefactor will change. And now you can actually take the same prefactor out, and because of, but first you notice that these are the same 4-point function that we are computing, but in two different ways. So therefore these has to be same, right? And Bootstrap equation is nothing but demanding the equivalence between taking OPs in different ways. So this is I call S channel, this is I call T channel, and claiming that these two expansion has to be same will give us the Bootstrap equation. And this U by V to the power delta phi that you are sitting here, that you can see here, that is coming because you can see that the prefactor has changed. So therefore you have to take a factor out the same prefactor that appears here. And while you do that, you get this overall factor of U by V to the power delta phi. Okay.
I have a question.
Yes.
Yeah, so this implies that I can always find a separating sphere between operators. So not the case.
Your voice is breaking.
This another.
Sorry, I didn't get your.
Am I audible now?
Yeah. Now you are audible.
Am I audible?
Yes. Now you're audible.
So
no, again it is breaking.
This
sorry, you are not audible.
You are cracking. Maybe it's best you write in the chat and I can read your question.
Okay. All right. So we got the Bootstrap equation, and so initially, here you can see that this G delta L U V for identical scalars, actually they don't depend on the dimension of the field or anything. They just depend on the exchange operator dimensions, that is delta and the spin. And this part is the kinematical part, and it is fixed for any 4-point function of any theory you compute. You can always expand with the same G delta LUV. So this part is completely fixed. Okay. The only part that depends on the theory in the following sense, that this C delta L, that is the 3-point OP coefficient. And of course, when I say that this part is completely fixed, what I mean is that the functional form of this is completely fixed, but you don't know what are the specific values of delta and L in your theory, right? So that is what comes from out of the computation. But yeah,
so the question was that he's asking that can we always find the separating spheres?
Yeah, I mean, for this kind of configuration, I can always bring these two together, unless, yeah, I mean, I can do the conformal transformation and bring two of them close together, and yeah, I mean, at least for this kind of configuration, I can believe.
Next question is, what if the points are collinear?
What if the no? So I'm going to do a conformal transformation and bring them close together. If you don't allow me to change, then it will not happen, right? But I can do a conformal transformation on this and bring
There is another question which says that what about the OP we get clubbing phi1, I mean phi at x1 and phi at x3?
Yes, I mean, that is called U channel. You can take the thing again, and that is again given by the same block that you are seeing here, but U and V will change to 1 by V and U by V. So that is called U channel. But the fact is that if you study the identical scalars, then if you consider the bootstrap equation that you get out of that kind of OPs, which is U channel OP, and you relate it to S channel or T channel, that doesn't give you anything like any constraint other than that all the spins has to be even. So the only constraint you get out of that bootstrap equation would be that only even spins can appear in the spectrum of this theory for these 4-point correlators. But indeed, you can consider that, and that has a valid conformal block decomposition. That is there actually. So this is the one that I'm writing is like more familiar in the sense that this is the one that gives you non-trivial constraints. Let's put it this way. It's not that the other one doesn't give you that also gives you the constraints, but that just tells you that there has to be even spin in the spectrum. Okay. All right. So what I have just
so there is a question that when you said that using the conformal transformation you can shift the point. So the question they have asked that, can we explicitly prove that there always exists such conformal transformation?
Can I explicitly prove that there exists? Yeah, I mean this. So I can always bring 3 points like this. So that is something that is proof that I can take any 3 scalars, and I can. Sorry. So I can take any 3 operators, and I can always put one of them to 0, one of them to 1, and one of them to infinity, and one of them on this plane. Okay. So suppose when I want to consider the thing the OP between phi x1 and phi x2, what I will do is that I will put the phi x1 at 0, phi at x3 at 1, and phi at x4, which I will send to infinity. And then x2 I will bring here. So which is basically ZZ bar is between 0 and 1. So then I can always draw a sphere between these two, and I can take the OP of this, and then I can take the OP of this. Now, suppose that is not the case, then what I will do is that I will put the phi at x1 at 0 and x3 at 1, and I will send the x2 to infinity, and then phi at x4 would be here. So then I can consider the phi at x1 and phi at x4 and do the OP. So this particular, so you can think of like, you can always do this to any operators that you have, at least
Okay,
for at least for 4 points. 4 points. That's yeah.
There is another question that regarding the condition of convergence of OP. So should the sphere have one of the insertions at the center?
No. You just have to draw a sphere that separates these two. I mean, these two operators need not be at the center of the sphere. That is not. You just have to draw a sphere that separates these two from other twos.
Why is that one of the points is arbitrary, but the other 3 are fixed?
Oh, this is so after you fix these 3 points, actually the only symmetry that is left is basically so you don't want to shift these 3 anymore. So therefore you can take a rotation about this axis. So basically this point has to be on this plane. If you do any other transformation, then these 3 points will shift, and you don't want that. You want to keep these 3 points fixed. And so then the only degrees of freedom that is left to this point is on this plane.
Okay.
So you wrote down the bootstrap equation, right?
Yes.
Is there any like what is being bootstrapped here? Like what are we bootstrapping?
So it's basically, at least to me, what it means that you are getting a consistency condition. Okay. You are getting a consistency condition in this equation, and the dynamical data of your CFT, that is the OP coefficient and the dimension and the spin of the operator, they have to be such that this equation holds, this consistency condition holds. So that in that sense, this is like bootstrapping. This is a bootstrap. So this is a self-consistent equation. Yeah. So if you like, we are bootstrapping basically this 4-point function, right? I mean, we are writing the expression for 4-point function in 2 different ways, and then we are using that as a constraint for the OP data.
I see. I see. Okay. Thank you.
All right. So, okay. So let me just, since we are out of time, so let me just quickly tell two consequence of this bootstrap equation. For example, like you might be wondering, like, what are the things that we can get out of this bootstrap equation? So one of the important thing of this, one immediate consequence of this bootstrap equation is the following. So you wrote down this bootstrap equation, and I told you that you know these functions in principle. Okay. So now if you study this equation in the limit when u is tends to 0 and v tends to 0. Okay. So you should remember that u was z bar and v was 1 minus z bar. Okay. So when the u goes to 0 and v is also goes to 0, at that limit, what happened is that this g delta L up, which is on the left hand side, that behaves roughly like u to the power delta minus L by 2 times some function of v. Okay. And then on the right hand side, you have this spectrum. So now you take the identity operator that you have in the theory. Okay. So then for the identity exchange, the OP coefficient is 1, and this block also evaluates to 1. So what you get is that just a simple function u by v to the power delta phi. So now you can see that if this has to be consistent, then your whatever theory you consider, this is telling you that if you have a scalar, then whatever theory you are considering, irrespective of that, because of the presence of identity operator, um, this twist, there has to be some operator for which the twist would be 2 delta phi. Because so twist is basically this difference between the conformal dimension and the spin, and that has to be 2 delta phi. Otherwise, these powers won't match, right? So therefore, you immediately get a consequence of the bootstrap equation that I must have operator with twist 2 delta phi in the spectrum whenever we have an identity in a unitary CFT. Okay. So this is a very powerful statement, because without going into a specific theory, you are telling a general you are talking about the spectrum of the theory. So this is of course leading order. I mean, it will receive quantum corrections and so on, but there has to be some operator which has dimension like this. And in fact, you can prove by looking at so this is the leading term. You can, by studying the other terms, you can prove that only 2 delta phi won't be enough. Rather, you need some operator like 2 delta phi plus 2n, where n goes from 0 to infinity, all the integers, non-negative integers. Okay. And another thing is that, so this is some details that basically you might be wondering that what happens to v goes to 0 limit. And you can see that in the v goes to 0 limit, this term diverges as v to the power minus delta phi. So this is like a power law singularity. On the other hand, if you look at the behavior of this f delta LV, this guy goes as log v. So you have a contradiction between these two sides. One guy goes as log v and the other guy goes as v to the power minus delta phi. But you should notice that there is a sum. So therefore, before comparing, probably you have to do the sum. And that is what turns out to be the case. So when you do a spin, like infinite spin sum on this side, then the divergence of this block enhances. So instead of going it like log v, you will reproduce the same as 1 by v to the power delta phi behavior out of this exercise also. So what it means that by summing over infinite operators on the S channel, you can reproduce the identity operator of your T channel. Okay, so this is one particular application of Bootstrap equation. Now these are my last slide. So I just this I will not tell you in any details, but I want to finish with this, that so you can write down the Bootstrap equation. And so this is just rewriting the Bootstrap equation that we have already written. And then the claim is that okay, so in the phi OPE there is an identity operator in unitary theories, and then there is a let's say there is a scalar operator and plus some other spinning operators, scalar operators, and so on. But this is the lowest scalar of the OPE which appears after identity. Okay. So now the thing is that the people what they have achieved to show is that they can play with this equation and put a bound on this on the on the largest dimension that this delta can get. Okay. So the plot that I'm showing you here, which is taken from this paper, this is telling you that if the theory has to satisfy this crossing symmetry, if my CFT data has to satisfy this crossing symmetry equation, then this delta, which appears immediately after the identity, that can be as big as these blue lines here, for the particular delta phi values. So these are here you are varying the value of delta phi. So that is the dimension of the phi field. So the 4-point function you are considering. And then you are looking at the maximum gap that you can put on the value of this lowest scalar present in your OP. Okay. So what it is saying, that if your delta is somewhere here on the in the white region, then that can't be a consistent CFT data. So you can see that though you are not proving existence of a CFT, but you are ruling out CFTs. So what you are saying is that if the scalar operator delta has a value which lies in the this white region, then you can't have a consistent CFT solutions. So therefore that is ruled out. If you want a consistent solution, it must lie below this. Okay. And it turns out that these boundaries are pretty interesting. There are very interesting theories. For example, if you are doing this exercise in 3D, then there is a kink, and at this kink, the 3D Ising model appears, which also describes some physical systems. And it turns out that so what happened is that in this game, the thing that people do is that they act with some linear functional on this Bootstrap equation. So on this block. Okay, so this block I am calling this capital F, and then on this block you are acting with some linear functional, and you get some quantity like this, which is basically a real number for a particular value of delta phi and delta and L. And then the Bootstrap equation now turns into some functional equation, which is like C delta L, and then the action of omega on the F, and then you are summing over the spectrum, and that gives you 0, right? Now, the way they look for it is the following: that suppose the action on the identity operator is greater equal to 0, and then if delta is greater equal to delta star, then the action on this is also greater equal to 0. And suppose so this is, you can see that this is nothing but the unitarity bound for non-zero spins. So for those cases, sorry, here it will be 0. So suppose the action of the of this functional on the Bootstrap equation is also greater equal to 0, then what you can show is that if it is greater than delta star, then basically there would be no solution, because everything would be positive, and you can't add up positive numbers to get a 0, right? So therefore this would be a inconsistency. So that's how actually they tackle the problem. And if you are wondering what these omegas are, they are nothing but they are some differentiation operator. So you are basically taking derivatives of your Bootstrap equation at some suitable point where the convergence is better and so on. But the point is that all these results are numerics. Okay, you might be interested to actually solve the theory which lies in this boundary, because there are many interesting theories. And also you might be interested to derive the bound, this bound. So this maximum gap of the on this operator having dimension delta, you might be interested to derive that analytically. For that, actually, you need to find out suitable other functionals. Like this derivative functionals are no good for that. I mean, it only works better for numerics. Okay. So that sort of thinking, like trying to derive, these are called optimal bounds. So the bound, like the highest gap that you can put on the scalar operators. So so what I'm trying to say here is that those kind of thinking, that how to derive those as analytically, will lead us to a very different kind of point of view that one can take on the Bootstrap equation of these 4-point correlators. Namely, you can see that this S channel equal to T channel kind of things were not manifested in our usual Bootstrap equation, and we solved the equation. So those kind of symmetries would be automatic, and it will not be consistent with the OPE, and you will get out of this new kind of sum rules. Okay. So all these things will appear out of asking these kind of questions, and that will be answered actually in Miguel's lecture, like what other functionals one can consider that will act on the Bootstrap equation and potentially help us to derive these optimal bounds analytically. So that is, I think, will be answered there. So you should listen to that. And that's it. Yeah, thank you. And you can ask questions now, I guess. So.
Hello.
Yes.
Hello. So
Yes.
you said when we get to get the differential equation involving the Casimir, you
Yeah.
said that we have to add the Casimir on the 4-point function, right?
Right. Yes.
So why only the 4-point function? Because Casimir is this is an eigenvalue equation, right? So any function can be written like that, right?
I'm sorry. Probably I'm missing your.
No,
Yeah.
my
Can you tell
question.
that again? Yeah. Can you
My
tell that?
question is why we have to act on the 4-point function specifically. Can we not act on any?
Yeah, sure. I mean, this is where we are interested in deriving the blocks where we can expand our 4-point function. That is why we are acting with this. But suppose you want to act on some 5-point function or something, yes, of course you can do that.
So can we do for a 2-point or 3-point function?
You can act with the Casimir operator. Yeah, you can act with that.
Okay.
Yeah, I mean, you see, I mean, the point is that Casimir operator, when acts on the state, that gives me this thing, right?
Yeah.
So that's what I use to say that, okay, so G delta L UV is nothing but basically some primary operators plus some descendants. So if C acts on them, I should get back the same eigenvalue equation. You should notice this is the same as what appears there.
Yeah. Okay. Thank you.
Okay, are there any other questions? Okay, if not, let's thank Kausik again for a very nice introduction to the dynamics of the CFT. And we will meet again on Friday at 5 p.m. to commence Miguel's lectures.